Pragya Sharma from ABS Engineering College, Ghaziabad. In this lecture series, we are covering Unit 4, Introduction to Fluid Mechanics and Applications. This is of subject Fundamentals of Mechanical Engineering. So we have covered the Introduction to Fluid Mechanics, basics of fluid mechanics in previous lecture videos. In this lecture video, I'll be covering the part of turbines in this video and further videos. The application part will be covered. So, first we will start with hydraulic machines. What are hydraulic machines? Hydraulic machines are defined as those machines which convert either hydraulic energy, which is energy possessed by water, this is hydraulic energy. These are defined as those machines which convert either hydraulic energy into mechanical energy, which is further converted into electrical energy, or these machines can convert mechanical energy into hydraulic energy. The hydraulic machines which convert the hydraulic energy into mechanical energy are called turbines, while those hydraulic machines which converts the mechanical energy into hydraulic energy are called pumps. Here we are categorizing two types of hydraulic machines. The one type of machines which are converting the hydraulic energy of water into mechanical energy, that is further converted into electrical energy. These are termed as turbine. When these machines are converting the mechanical energy into hydraulic energy, these types of hydraulic machines are termed as pumps. These are the two types of hydraulic machines. One is turbines and the another one is pumps. So what are turbines? Turbines are defined as those hydraulic machines which are converting hydraulic energy into mechanical energy. This mechanical energy is further used in running an electric generator, which is directly coupled to the shaft of the turbine. This type of mechanical energy, the converted mechanical energy, is further converted into electrical energy. Thus, this mechanical energy is converted into electrical energy. The electric power which is obtained from the hydraulic energy. This hydraulic energy, what is hydraulic energy? It is the energy possessed in the water. So this electric power which is obtained from the hydraulic energy is known as hydroelectric power. So these are turbines which are basically converting the hydraulic energy, the energy of water, into the mechanical energy. So here a general layout of an hydroelectric power plant is given here. So we can see in the figure, the hydroelectric power plant is here. This is a general layout of an hydroelectric power plant. So this is the general layout of a hydroelectric power plant. So first, a dam is a dam constructed across a river to store the water. This is a dam. This is a dam which is constructed across the river where the water is stored. Here is the water which is stored. So pipes of large diameters are called penstock, which carries water under the pressure from the storage reservoir to the turbines. This is the storage reservoir where water is stored. This is the dam, the construction to store the water across a river. Then this is the pipe. This is the pipe of large diameter from where the water can be traveled from reservoir to the turbine. This here, the turbine. This is the turbine. This is the penstock from which water comes towards the turbines. So these pipes are made of steel or this can be made of reinforced concrete. Turbines having different types of vanes fitted on the rotor or fitted to the wheels. These are the different types of vanes. These wings type structure. This is vanes. These are vanes. These are mounted on the wheel. Tail race, which carries water away from the turbine after the water has worked on the turbine. This is tail race where the water leaves after working on the turbine. So here the tail race. So this is a general layout. There are some heads are given. Now we will be discussing the we will be discussing the heads of the turbine. So these are like here the heads of the turbine. First is gross head. What is gross head? The difference between the head race level and tail race level where no water is flowing is known as gross head. This is head race level. Sorry. This is head race level and this is tail race level. The distance between head race level and tail race level where is no water is flowing. This is gross head, HG. This is gross head. Then net head. What is net head? Net head is also called as effective head, and it is defined as the head available at the inlet of the turbine. Available at the inlet of the turbine. When water is flowing from head race to the turbine, there must be a loss due to friction between the water and penstocks. There must be a friction. There must be a loss of head due to the friction between water and penstock. Through there must be some other losses also, like loss due to bend, pipe fittings, loss at the entrance of penstock. There must be other losses also, but they are very small in magnitude as compared to the head loss due to friction. So we are considering the head loss due to friction only. Other losses are very small. So those are not considered. So HF is the loss of head due to friction. So HF is considered here. If HF is the head loss due to friction between penstock and water, then the net head is H net. Net head will be equal to gross head minus head loss due to friction. This is gross head denoted by Hg, and this is HF, friction head, head loss due to friction. So net head will be equal to Hg minus Hf. So now we are discussing efficiencies of turbine. We have already discussed the heads of turbine. The next topic is efficiencies of turbine. There are following are the important efficiencies of turbine. First is hydraulic efficiency, which is denoted as eta H. Then second one is mechanical efficiency, that is denoted by eta M. The third one is volumetric efficiency, that is eta V. And the fourth efficiency is overall efficiency, that will be denoted as eta O. So first is hydraulic efficiency. It is defined as the ratio of power given by water to the runner of a turbine. Runner is a rotating part of a turbine, and on the runner there are vanes are fixed. We have already seen in the layout of the turbine, there is a wheel, that is runner. The vanes are fixed on that runner. So the hydraulic efficiency is defined as the ratio of power given by water to the runner of a turbine to the power supplied by the water at the inlet of the turbine. The water flows from the penstock and hits the runner. The runner starts rotating from the water's energy. There must be a force by which the runner starts rotating. And so what is the power delivered to the runner? The ratio is hydraulic efficiency. It is defined as the ratio power given by the water to the runner of a turbine to the power supplied by the water at the inlet of the turbine. The power at the inlet of the turbine is more and this power goes on decreasing as the water flows over the vanes of the turbine due to there must be some hydraulic losses as these vanes are not smooth. So these losses will be considered. So mathematically, we can write hydraulic efficiency is power delivered to the runner divided by power supplied at the inlet of the runner. So this is hydraulic efficiency. Next is mechanical efficiency. Due to mechanical losses, the power available at the shaft of the turbine is less than the power delivered to the runner of a turbine. So, the mechanical efficiency can be defined as the ratio of power available at the shaft of the turbine to the power delivered to the runner. So, it is written here mechanical efficiency is the ratio of power at the shaft of the turbine divided by power delivered by the water to the runner. Next is volumetric efficiency. The volume of the water striking the runner of a turbine is slightly less than the volume of the water supplied to the turbine. Some of the volume of the water is discharged to the tail race without striking to the runner of the turbine. So that is considered here. The water goes directly into the tail race without striking the runner of the turbine. Thus, the ratio of the volume of the water actually striking the runner to the volume of the water supplied to the turbine is termed as volumetric efficiency. We are considering the water which is not used at the runner and that directly goes in the tail race. So, volumetric efficiency is equal to volume of the water which is actually striking the runner and volume divided by volume of the water which is supplied to the turbine. This is volumetric efficiency. Next is overall efficiency. What is overall efficiency? It is defined as the ratio of power available at the shaft of the turbine to the power supplied by the water at the inlet of the turbine. Basically, efficiency is output by input. What is the input of the machine and what output is provided by that particular machine. So overall efficiency is what is the power available at the shaft of the turbine, the output of the turbine, which is power available at the shaft, and divided by input of the turbine, with the power supplied by the water at the inlet of the turbine. This is overall efficiency of a turbine. These are the four efficiencies of the turbines. Next topic is classification of hydraulic turbines. The following are the important classifications of the turbine. First, we are classifying on the basis of the type of energy at inlet. On the basis of type of energy at inlet, we can categorize in two types. One is impulse turbine, another one is reaction turbine. If the turbine wheel is driven by the kinetic energy only of the fluid that strikes the turbine blade through the nozzle, then the turbine. That is known as impulse turbine. It is using the kinetic energy of the fluid to rotate the wheel of the turbine, to rotate the runner of the turbine. That is impulse turbine. The example of impulse turbine is Pelton wheel turbine. The another one is reaction turbine. The energy of at the inlet is used, the sum of the potential energy and kinetic energy of water. It means the potential energy and kinetic energy both are used at the inlet of the turbine, which are due to pressure and velocity respectively. This causes the turbine blades to rotate. These type of turbines are called as reaction turbine. The examples are Francis turbine and Kaplan turbine. Next is the second classification is on the basis of direction of flow through the runner. In which direction the water is flowing through the runner. One is tangential flow turbine. When the water flows in a tangential direction to the runner, these are termed as tangential flow turbine. Example is Pelton wheel turbine. The second one is radial flow turbine. When the flow direction of the water is radial direction of the runner. When the flow in the runner moves radially, these turbines are further divided into two types. One is inward radial flow and another one is outward radial flow. Francis turbine can be an example of radial flow turbines. Then third type of is axial flow turbines. What are axial flow turbines? When the fluid flows parallel to the turbine shaft, it means the turbine axis, shaft axis. The fluid flows parallel to the shaft axis. The example is Kaplan turbines. These are axial flow turbines. The last type is categorized as mixed flow turbine. What is mixed flow turbine? In this type of turbines, the flow enters the turbine radially, but it exits or it leaves axially. So this is mixed flow. There are two types of flows. At the time of entry, the flow is in radial direction. At the time of exit, when the fluid leaves, it is axial direction. So these are termed as mixed flow direction. Mixed flow turbines. Example is modern Francis turbines. Third we can categorize according to the heads at the inlet of turbine. So there is high head turbines, medium head turbine, and low head turbine. In high head turbine, when heads are higher than 250 meters, these are termed as high head turbines. Like a Pelton wheel turbine is a high head turbine. Then medium head turbine, when working range of heads are 45 to 250 meters, this is medium head turbine. These are like Francis turbine is a medium head turbine. Then when the head range is lesser than 45 meters, these are termed as low head turbines. Kaplan turbine is an example of low head turbine. The fourth category on which we can classify the hydraulic turbines are on the basis of specific speed of a turbine. So there are three types of turbines on the basis of specific speed. One is low specific speed turbines, another second one is medium specific speed turbine, third one is high specific speed turbine. We can categorize like if the specific speed is less than 50 rpm, there is that will be termed as low specific speed turbines. Then it varies from 50 to 250 rpms. It comes under medium specific speed turbine category. And when the specific speed is more than 250 rpm, that will be termed as high specific speed turbines. These are the classifications of hydraulic turbines. So these are references. Some books are there. These are the references. And in further videos, we will covering the turbines, Pelton wheel turbine and Francis turbine. Thank you.